So next, starting in on our next equation solving lesson, and as we've been doing each time, we just want to quickly overview how this fits into whatever course you might be in. This particular lesson is extremely applicable for all of Math 038, 052, and 053 students. Most specifically, it is part of Chapter 3 in Math 053. However, Math 052, Chapter 4, you have to do literally everything that is in this lesson as well as Math 038, everything that is in today's lesson. So I am calling this Working with Formulas Part 1. We will go on to Part 2 and Part 3. Parts 1 and 2 are relevant for Math 038 and 052 as well as 053. Only the third part is really just a Math 053 topic that when we get to that one. That won't be till the last lesson in the next class. If you're in an 02 level class, you will see some stuff here that you recognize, the perimeter and volume formulas in particular. And so this is actually potentially useful for you when we move beyond those types of rectangles and triangles and into more complicated shapes. It's not something you specifically see in that course, but again, you're all heading towards Math 052, so it doesn't hurt to see how that's going to work out. Okay, so many everyday situations are governed by mathematical relationships. This is why we do math, basically. So things like, if you need to calculate the area of a triangle, which would be something you'd have to do really commonly, actually, in a lot of the trades, for example. There's a formula. The area of a triangle is 1/2 times the base times the height. Or if you have a cylinder, so like, a tank that's holding gasoline or water or something, calculate the volume of it. There's a formula for that. The perimeter of a rectangle. So if you want to build a fence around your yard, you're looking at the perimeter of your yard, right? And there's an equation to calculate the perimeter. If you're driving your car, then how far you travel is given by this formula: rate times time. Rate is just a different word for speed in this context. We use R for rate because then it applies to all kinds of other situations besides just a moving car. But if you're going, as this diagram shows, 40 kilometers an hour as your speed, and you drive for, say, 3 hours, how far did you go? You went 40 kilometers in the first hour, 40 kilometers in the second hour, 40 kilometers in the third hour. You went 40 times 3, 120 kilometers. And there's that formula right there, 40 times 3, rate times time. Excuse me. And also, if we get into things like finance, this is a formula for how much interest you earn on something like, say, you decide to put your money in a GIC, that's a guaranteed investment certificate, where you tell the bank, I don't think I need this money for a year, and I want to earn a higher interest rate. And they say, sure, sounds great. They take your money, they stick it away, and you're not allowed at it for a year. But when you do, this is how much interest you would earn on that money. Principal times the interest rate times the time. And we'll look at all of these various ones. Will come up probably in our examples somewhere or other. So you're going to be asked to use these formulas to calculate values of the various variables in them. And there's one of two main scenarios where that will happen. And again, this is all of the courses, the 03 and 05 level courses, you will be asked to do this. Scenario 1 is the easy one we're going to look at today, where the variable that you are asked to calculate is already the one that is isolated on the left side. So if I look back at this list here, in the first formula, the A is by itself already. In the second formula, the V is by itself. In the third one, the P is by itself, right? So in each formula, there's something already isolated on the left-hand side. And in that case, you just plug in all the other values and do the calculation. And that's what we're doing today. Scenario 2, we're going to look at next time, where the variable that you were trying to find is not the one that is isolated. And I say on the right side here, but I meant to say on the left side. Oh no, I should read my sentence. My sentence is good. The variable you are trying to find is one of the ones not isolated on the right-hand side. So if we look back at our list, maybe they'll ask you to calculate the height in this formula and give you all the other ones. Or maybe they'll ask you to calculate the length of a rectangle and give you the other information. So you're going to be using our equation solving in that case. And that will be our first lesson on Wednesday. Okay, so let's just do a bunch of these just to get the feel for it. So we've been told that the formula for the area of a triangle is given by a equals 1/2 base height. By the way, you do not need to memorize any of these formulas. Either you will be given a formula sheet in some courses, and in other courses, if you don't have a formula sheet that you're given, then any given question will tell you what the formula is. So you don't need to memorize any of these. So B is the base of a triangle. That is the flat distance along the bottom here. H is the height, which is straight up and down up to the highest point from the bottom. So here we've been given a triangle that has a base of 6 centimeters, a height of 8 centimeters, and we've been asked to find the area. So step 1. And you're going to see this in every single example we do for all 3 parts of the Working with Formulas lessons. Step 1, just write the formula down. Do it. Write it down because you're going to potentially have to work with it. Some people want to just pick up their calculator and start punching, and here's what happens. It works on the easy ones, and so they're like, great, this is easy. I don't need to do all this writing the formula down. And then it completely falls apart when you have to work backwards. So write the formula, step 1. Step 2 will again be the same for all of them. Sub in everything you know. So in this case, we have been told that the base is 6 centimeters, which I put in red there. So I replaced the B with a 6. And the height in blue is 8 centimeters, so I replaced the H with an 8. Again, you see how my equal signs always line up. So the area is 1/2 BH. We plug in the numbers we know, a 6 for the B and an 8 for the H. And step 3, since we already have the thing that we want by itself, we're looking for the area, it's already by itself on the left side of the equation, right? Since we already have the A by itself, all we got to do is work out the right-hand side. And usually you can just pick up a calculator for this. So you can do this in stages if you want, and you can do fraction work if you want, but once you're into this chapter, you're into the chapter or into the part of the course where you're allowed a calculator. So you can also just pick up your calculator. A half is 1 divided by 2. So punch into your calculator 1 divided by 2 times 6 times 8. And your calculator will tell you 24, just like that. And again, you can go slower. You can go a half times 6 over 1 becomes 3. And then 3 times 8 is 24. You can try that fraction work if you want. But really, that's not necessary at this point. And in fact, often these answers are not going to be nice whole numbers. They are going to be decimals, and your calculator is going to be necessary. Okay, 24. Now, we're never going to leave any of these questions without units. So in this case, the units are, we write centimeters squared. The way we say that is actually square centimeters, and that's our unit for area. Let's just quickly talk a little bit about units, because this little 2 up here that looks like a square does confuse some people, and they start to try to square things. Nothing gets squared. This is actually just a lazy way of writing what the unit is, square centimeters. So that's our answer. Yeah, let's talk about units very quickly. If we are measuring distances, they are in what we would call linear units, and we have all kinds of them. You pull out your ruler or your tape measure, and you measure how many centimeters long a line is, or how many inches it is, or miles, or kilometers, or feet, and so on, and so on, and so on. So there's a line that's maybe 8 centimeters long, like so. When we are talking about area, then we use square units, they are called. And what that means is you imagine taking a little box that is 1 centimeter by 1 centimeter, like that box right there, and then you ask yourself, how many of those boxes would it take to fill up the flat space that the shape takes up, like a triangle or a circle or a rectangle or a parallelogram or weird shaped things? How many of those little squares would it take to fill it up? And you see that it is a square centimeter, right? Is literally what it is. And then mathematicians, as we keep saying, are incredibly lazy, and they're like, oh, I don't want to write square centimeters every single time I do an area question. So they said, hey, let's just write it like that. Centimeters, and then with the little squared sign. But notice nothing is getting squared. Again, some people will take their answer and square it. No, no, no. The centimeters squared is just units. That's all it is. It represents square centimeters, and we're simply saying how many of these little squares here does it take to fill in that flat shape. So for example, there's a rectangle, which is 4 centimeters by 2 centimeters. If I were to put a whole bunch of little square centimeters in there, notice this is now a distance of 1, 2, 3, 4 centimeters, and this is a distance of 1, 2, right? And then shade those in, we see that there are 8 square centimeters that it takes to fill up that shape. Therefore, the area of that shape is 8 square centimeters, written in our lazy way with the little square sign, which does not mean we go 8 times 8 is 64, right? We do not square anything. It is just a lazy notation for how many of these little squares does it take to fill up whatever shape you happen to have. Centimeter squared is simply notation. Nothing actually gets squared. And then if we move on to volume, then with same idea, but we are now in cubic units, centimeters cubed, inches cubed, miles cubed, so on. And that is the exact same thing, but instead of a little square that is 1 centimeter by 1 centimeter, you would have, imagine a little cube that is 1 by 1 by 1. And then you want to know how many of those cubes does it take to fill up the shape. If the shape is a funny shape, like a bowl or a sphere or whatever, any kind of weird shape, you could imagine that these little cubes are made out of plastic. And you're going to melt them all down and pour them in and see how many of those melted down cubes does it take to fill in that weird shaped bowl or whatever it is. And that is the idea of volume. So distance, straight line, linear units without any power. Area, flat spaces like triangles or rectangles or circles. How many squares, centimeters or square inches or whatever it is does it take? You could think of it as paint as well, right? To paint the flat area. Volume, cubed units. How many can you pour into some three-dimensional shape to fill it up? 1 cubic centimeter, we call it 1 centimeter cubed for short, but again, nothing actually gets cubed. It's just notation. Okay, so let's carry on with some more examples. So the volume of a box type shape is given by the length times the width times the height, V equals LWH. And so here we have a fish tank, which has a length of 22 inches, a width of 10 inches, and a height of 4 inches. We want to know what volume of water can we pour into that tank. Step 1, write down the formula, like so. Step 2, fill in all of the values which we know, which in this case is the L, the W, and the H. So there, the length in red is 22, the width in blue is 10, and the height in yellow or orange is 4. And we notice again, like we're going to see in every example in this particular lesson, that we know everything on the right-hand side, and the thing we're looking for is on the left-hand side. That is going to change in the next lesson, where we will know the volume, but maybe be looking for the length or the height or something. So all we got to do is multiply those 3 numbers together. Since V is already isolated, simply calculate the right side. 22 times 10 times 4 on your calculator. No need to do this by hand at this point. 880 cubic inches. And again, the inches cubed is just notation for volume. We're saying how many little plastic 1 by 1 by 1 cubes could we fit inside that fish tank to fill it up? And it would be 880 of them. Here's a circle, and we are told that the area of a circle is area equals pi r squared. And again, you do not need to memorize these formulas. If you're in 038 or 052, you will be given a formula sheet that you can have on the test. If you're in 053, any question will tell you what formula to use. They will not, you don't have to know them by heart. A equals pi r squared. So what is the area of a circle with a radius of 7? And we've been told just to use 3.14 for pi. Oh, one day if we have time and you want to hear me ramble on and on, get me to talk to you about pi. It's a very interesting number. All kinds of fascinating things. But we're just going to shorten it. We know it goes on forever. It's an irrational number. But 3.14 is generally close enough for anything you want to use for a real world calculation, unless you're like trying to fly people to the moon or something. So step 1, write the formula. A equals pi r squared. Step 2, fill in all the values we know. Well, we know what we're going to use for pi, and we know what the radius is. The radius is 7. So in blue, I replaced pi with 3.14. In red, I replaced the r with 7. Watch out for probably the most common little twist on this question is that instead of telling you the radius in the diagram, they show you the diameter, which would be 14 meters. Diameter is the distance all the way across the circle. The radius is the distance from the center to the edge. So if they give you 14 for the diameter, you got to cut it in half to get the radius of 7. And now we're going to evaluate this order of operations. We got to do that exponent first. So 7 squared is 49. And now we can just multiply 3.14 times 49, and we get 153.86 square meters, or meters squared, because it's an area, so the units must be in square units. Okay, here's a cylinder. Oh, we got you trying this one. Okay, so let's, do I gotta pause the video? Yeah, I do. Okay, so give this one a try. I'll give you 2 minutes for it maybe. You've given you the formula, v equals pi r squared h. And notice we did throw that extra little twist in here. They've given you the diameter is 42 feet, but you got to divide that by 2 to get the radius, which is what actually goes in the formula. So why don't you give this one a try. So first thing we notice is that the formula asks for the radius, but we've been given the diameter. So we divide by 2, and we get that the radius is 21 feet. Now we're going to follow our steps. Step 1, I haven't listed the steps this time, but we'll still follow them. We are going to write down the equation, v equals pi r squared h. Step 2, we are going to plug in everything we know. So in blue, pi is 3.14. In red, the radius is 21. And in orange, the height is 110. So we fill all those numbers in, and notice, as always, when we plug in numbers, we put brackets around them, because often that's going to be important for the exponents or the multiplication. So each of those things we plugged in, we put in with a bracket around it. And now we are simply going to work out the right-hand side, because, again, notice that the thing we want is by itself already, and we know everything on the right. So again, I see order of operations. I got to do the 21 squared first. On my calculator, I get 441. And now let's multiply those 3 numbers together. And again, you can just do that in one shot on the calculator. And assuming I made no mistakes, I get 152,321.4. If you ever catch anything wrong in any of these, let me know. So there is the volume of that gigantic, looks like some kind of a storage container or a grain silo or something. So if you had boxes that were 1 foot by 1 foot by 1 foot length, width, and height, you could pour 152,000 of those boxes. You could throw them into that cylinder. That's how many it would hold. Now, of course, it's not perfect because of the rounded edges, but if you could, like I said before, if they were plastic and you could melt them down, that's how many you could pour in there. Okay, so let's carry on. We're going to look at a car one here. So the distance a car travels is given by the formula d equals r times t, where r is the rate that the car travels, in other words, its speed, and t is the time that you drive. So if you are going at 72 kilometers an hour for 3.5 hours, 3.5 hours, how far did you go? Step 1, write down the equation. D equals R times T. Step 2, sub in all values that you know, which continue for today to only be the values on the right-hand side. R becomes 72 and T becomes 3.5. And step 3, work out those numbers, and in this case it's just a simple multiplication. 72 times 3.5 is 252 kilometers. So if you drive for 72 kilometers an hour for 3.5 hours, you will go 252 kilometers. And I think I got two more for you to try. So, and the ones there is a little bit bigger equation. So yeah, why don't we just take 5 minutes just to make sure you have a chance to actually give this a try on your own and attempt those 2 questions, see how you do, and then we'll do them together. Okay, so let's take a look at these. This first one's a bigger equation, so there's more multiplying and powering and adding and stuff, but it's otherwise it's really just the same idea. So the surface area of a cylinder given by A equals 2 pi r squared plus 2 pi r h. If you're interested, maybe not. Well, sure. The 2 pieces, this piece here represents the top and the bottom, which are both circles, right? Each one is a pi r squared. That's why it's 2 pi r squared. And this piece here represents the side. So if you're like a tin can, you have the top and the bottom, and then you have the side. You could imagine peeling like the label off of that can, and then spreading it flat and calculating the area of that, and then adding on the circle on the top and the circle on the bottom. That's kind of how this formula works. Not that that necessarily matters for this question, but it's just kind of interesting maybe. So we want a surface area of a cylinder which has those dimensions. So step 1, write the equation we're going to use. Step 2, fill in everything we know, which I have, as usual, color-coded. So the pi in blue, both pi's got replaced by 3.14 in a bracket. The radius appears twice as well. It got replaced in both spots in red by 15 in a bracket. So this one you see is squared, but this one is not. And then the height is 32, so we replace the h with 32. So step 1, write your equation. Step 2, plug in everything you know. For today, everything you plug in will be on the right, but we'll see on Wednesday that sometimes you will know the thing on the left and you won't know one of the things on the right. Now let's work this out. We definitely got to think carefully about order of operations. This plus here between them, that's the last thing we're going to do. The first thing we're going to do is this exponent, 15 squared, so that's 15 times 15, 225. Now I have 3 things multiplied here and 4 things multiplied here, so I'm going to do all that multiplication. 2 times 3.14 times 225. I get 1,413 for that first piece. And then for the second piece, 2 times 3.14 times 15 times 32. That multiplication there, right, gives me 3,014.4. And now I can add those 2 together to get 4,427.4. What are the units? It's area, so the units are square centimeters in this case. And yeah, so what does that mean? If you had little stickers that were 1 centimeter by 1 centimeter, and you wanted to cover this entire can, right? That's what a cylinder is. It's just like a tin can with those stickers, including all around the side and the top and the bottom. It would take about 4,400 stickers to cover that whole can. That's the idea of what a surface area is, as opposed to volume, which would be how much soup you can pour into that can or pour out of that can. And let's jump over here to our last one, which is switching away from geometry and into finance. So interest is equal to principal times the interest rate times time. And I guess, again, this is called simple interest. More commonly in your life, you will run into compound interest, where you earn some interest this month, and then next month you earn interest not only on your investment, but also on the interest that you had already earned, and it grows like that. But there are some things, such as we talked about, guaranteed investment certificates, GICs, that do operate on simple interest. So step one, write the formula we're going to use. Step two, fill in the numbers. We were told that the principal is $25,000. The rate is 9%, which, remember, is 0.09. We have to put that in decimal form. And we're going to do this for 5 years. So if you had $25,000 to spare, and you put it in a 5-year GIC, this is how much interest you'd get. Anyways, let's do the calculation. We punch it straight into our calculator. 25,000 times 0.09 times 5. We get $11,250. That's not bad return if you could get a 9%. Well, you're never going to get a 9% GIC, but if you could get that rate from someone, that's not a bad investment to make, actually, if you can spare the money. All right, and I think, yeah, so next time we are going to look at what happens when the variable that we want to calculate isn't the one that's already isolated, which means we're going to need to use equation solving to isolate it.